All right, let's talk about the stunning OLED TV you might have in your living room. We're going to dive into this one ingenious trick that actually made them possible. It's a really cool story about a huge manufacturing problem and a solution that was, believe it or not, kind of hiding in plain sight.
So, have you ever really looked at an OLED screen and wondered, how does it look so real? Well, it's all about how they make the picture. Unlike the older TVs that needed this big backlight, every single pixel on an OLED screen is its own tiny little light. And that one difference, that's the key to everything.
Okay, so here's the real advantage. Think of an LCD screen like a window with the blinds always down. It's trying to block the sun, which is always on, but some light always leaks through. That's why the black on an LCD is more like a dark gray. But an OLED pixel, it's like a tiny light bulb. To make black, it just pop, turns off completely. No light means perfect, absolute black. This gives them what's called an infinite contrast ratio, and it's what makes the picture just pop with this crazy realism.
Okay, so if this tech was so amazing, why did it take forever to get big screen OLED TVs? You'd think they'd be everywhere, right? Well, for years, trying to make them at a large scale was just a total nightmare, both financially and for the engineers. Which brings us to this, the giant screen challenge.
So the problem wasn't the idea of OLEDs. The real issue was just making them without any screw-ups. This is measured by something called production yield. Basically, imagine this giant sheet of glass they use to make the screens. Even a tiny microscopic speck of dust can create dead pixels, and boom, the entire screen is junk, unsellable.
And this is where the math just starts to get brutal. Let's say you have a huge sheet of glass with just 3 random little defects on it. If you cut that sheet into 20 small phone-sized screens, yeah, you might lose a couple of them, but you still get an 85% yield. For a factory, that's a good day. That's a successful run.
But what happens if you try to make bigger screens? Say 4 tablet-sized ones from that same sheet of glass. Well, those same 3 tiny defects now have a much, much higher chance of ending up on one of your panels. And just like that, half your products are ruined. Your yield just nosedived to 50%.
And this is the wall they slammed into. When you try to make just 2 big TV-sized screens, those 3 defects are almost guaranteed to mess up both of them. Your yield crashes to 0. I mean 0%. Think about that. You're spending millions on equipment, on materials, and you're producing absolutely nothing you can sell. It was economically impossible.
It all boils down to this simple, brutal fact. The number of things that can go wrong just explodes the bigger the screen gets. A 32-inch screen has 256 times the area of a little 2-inch screen, which means it has 256 times the chance of getting a fatal flaw. And let's be honest, our tolerance as customers for even one dead pixel on a brand new TV is basically 0. This was the puzzle they had to solve.
So to get past this impossible wall, engineers needed something totally new. They needed a scalable technology, a way to build these things that wouldn't be so fragile when they got big. This forced them to rethink the entire idea of a pixel, and that led to a really clever insight.
So the first big idea was this. Instead of trying to perfectly print these tiny individual red, green, and blue OLED dots, which was super hard, they did something different. They just laid down one big uniform layer of white OLED material. Then they slapped a simple color filter on top, kind of like how an LCD works. This was way easier and more reliable to manufacture. But it created a new problem. Those filters blocked a ton of light, which meant the screens were super inefficient and the colors weren't great.
And this is where the real aha moment happened. It came from a pretty simple observation, actually. Researchers analyzed thousands and thousands of photos, TV signals, you name it, and they found something fascinating. The huge majority of colors we actually see in the real world, they're not those pure, supersaturated reds or blues. Nope, they're muted, kind of grayish, almost white tones.
This discovery led to a revolutionary thought. Since our world is mostly black and white and gray, with just a little splash of color on top, why not design the pixel to work that way?
And that is exactly what they did. They took the standard red, green, and blue subpixels and they added a 4th one. This new subpixel was pure, unfiltered white. This RGBW, or white pixel approach, this was the game changer. It was built specifically to handle all those really common near-white colors with unbelievable efficiency.
So check this out. This one simple change didn't just fix the manufacturing problem. It actually unlocked a whole bunch of other performance benefits, which brings us to the payoff.
Okay, so why was this so good? Well, the power savings were just massive.
For a normal picture, this white pixel method used almost half the power. And the reason is simple, right? The white subpixel doesn't have a color filter blocking its light. So to make a gray or a white color, which we now know is most of the image anyway, the TV can just turn on that one super efficient subpixel instead of having to blast the red, green, and blue ones through those wasteful filters.
Then, to really perfect the whole system, the engineers fine-tuned everything. They actually changed the chemical recipe for the white OLED light itself, adding a yellow element that our eyes are most sensitive to. And on top of that, they designed brand new, sharper color filters that could produce this huge range of vibrant, pure colors, all without giving up that amazing efficiency they just found. So this cable, it really lays out the whole journey perfectly. You can just see the dominoes fall, right? The big yield problem? That was solved by the white plus color filter method. But that created an efficiency problem. So they solved that by adding the white subpixel. And then finally, to get the color perfect, they optimized the light and the filters. It was this whole series of connected breakthroughs that turned an impossible dream into the TVs we have today. And this number right here, this proves it all worked. An early 8.1-inch prototype using this tech only used 1.5 watts of power. Now, at the time, a similar LCD was using 2, maybe 4 watts. This was hard proof that the new method could give you a way better picture while using less power. And that combination, low risk, high reward, that's what finally convinced companies to pour billions into building the factories that make the OLED TVs we all love today. You know, the story of the white pixel is just a perfect reminder that sometimes the most brilliant solutions are kind of hidden in plain sight. They just come from looking at a problem in a totally new way. I think the big takeaway here is that the tech in our lives is often built on layers of these clever, almost invisible tricks. And it really makes you wonder, right? What's the next white pixel out there that's going to change everything?